All right. Hello. Hello. All right. Good job, you guys. All right. So let's see what we got here. I'll make sure this is on. Yeah, there we go. Okay. Okay. Optimization. We're going over it. You guys already got the notes. Anyone missing the notes? Yes. Window seal. It's either window seal or under the blue box.
Are you talking about the review thing?
Mm-mm. 4.7. Is that 4.7 right there? No. It's either under the far TV. Keep going, keep going, keep going, keep going. Stop. Right there. There's a pile of paper there, right? Yeah, dig through there.
Let's start learning.
Okay, so optimization problems, which is a key to calculus. This is actually one of the big deals with calculus because there's certain things that calculus is always used for. One, related rates. Two, optimization, because you use it in business, you use it in all kinds of sciences and biologies and stuff. So optimization is a very good thing. Okay? Limits, you don't really use that very much at all outside. Okay? But this application of derivatives is super important. Okay, so read the problem until you understand it. Can identify the quantity for which maximum minimum value is to be found. Assign a symbol to represent it. So read the problem, find out what you're looking for, and if at all possible, draw something to represent it. The drawing is key. The drawing is key. Assign symbols to represent other variables of the problem. If possible, draw a picture, label it, determine a relationship among the variables. Okay? If it says that it is proportional, then you know that you need to set it up kind of like we did with the related rates with the triangles. Okay? Express the quantity to be maximized or minimized as a function of one variable and determine the meaningful domain of the function. Find the absolute maximum value or absolute minimum value for the function. So, one that you will always have, always, maximizing the area of some fenced in. So you have some pieces of fence, and you have so much of a perimeter, but you want to make the maximum area. So you need to arrange that so you will have the maximum area on it. So, let's go ahead and... Hey, look, here it was one right here. A farmer with 4,000 meters of fence wants to enclose a rectangular plot that borders a straight river. If the farmer does not fence the side along the river, what's the largest rectangular area that can be enclosed? Now, I have two different functions in this problem right here. What are the two different functions? Area and perimeter. Area and perimeter, right? Those are my two functions. I'm going to use one to substitute for the other. So, in this case, we already have a drawing. So, we have a river, and we have three sides on it. Okay, so now, I would write that my perimeter, so P is equal to 2x plus y, right? But my total perimeter, do I know what my total perimeter is? Yes. Say yes.
Yes. What do you mean 2y plus 2x?
4,000 meters.
Oh, never mind.
Yeah, that's my total amount that's going to go around it, all right? So that's super important. So I'm going to write that 4,000 meters is equal to this. So this is my perimeter part of the function. The next thing I'm going to have is area. Now, how would I find the area of that shape? So area, x times y. What are we maximizing? Area. So if I'm maximizing the area, that means I'm taking the derivative of the area. Taking the derivative of the area. But I only want to have one variable. I only want one variable. So I'm going to rearrange my perimeter part of my equation right here to replace one of my variables, either the x or the y. I recommend the y. Why would I recommend the y?
Because the X is a 2.
Yeah, x has a 2 in front of it, right? I don't want to divide it. I'm not going that far. So, all right. So for this part right here, what can I say that y is equal to?
Negative 2x plus 4,000.
Yes. All right, let's go 4,000 minus 2x. That'll work, right? Okay, so I'm going to rewrite it. So y equals 4,000 minus 2x. That's an equal sign right there. So that's going to be super helpful now. So I could replace what?
The Y
In my?
in that area right there.
Very good. So it's going to be A is equal to X quantity of 4,000 minus 2X. By doing that, what have I successfully been able to do?
Replace a Y as well another variable in your.
Yeah. So now I only have one variable, right? So if I'm trying to maximize, right? If I'm trying to maximize or optimize maximum, so think about it. I would take the derivative, and that has to equal 0, right? Mins and maxes. The derivative is equal to 0 for all mins and maxes. So let's go ahead and do my distribute. So it's going to be A equals 4,000 x minus 2x squared. I didn't have to do that, but I just wanted to. Insert page. So I have my area is right? Jess.
Yes.
Okay, so now I said we have to do what with this? Take the derivative. Let's do the derivative. So it's going to be dA dx, right? Why is this one dx instead of dt?
There's no time.
There's no time, right? And I'm taking the derivative to optimize my x value, right?
Yeah.
I'm optimizing the x value here. So that means I'm going to have 4,000 minus 4x. I need to set my derivative equal to 0. Let's do that. So 0 equals 4,000 minus 4x. Move that to the other side, so I get negative 4,000 equals negative 4x, right? Divide by negative 4, so x is 1,000. You good? Okay. All right. So x is 1,000. Yay. That's good. So now I know my x. So if x is 1,000, what's y going to be? Because look, right here, y is equal to 4,000 minus 2x. But if it's 2 times 1,000, that's 2,000. So that means that y has to be 2,000. There we go. What are my units? Meters. And, okay, this is optimizing a linear value. This is not an area yet. Okay, I just want the distance. I don't know what that total area is going to be. I could figure out the total area. Yeah, I could put in the total area, and it's going to give me a lot. 6 zeros. 2 million? Is that what it is? 2 million?
Yeah.
Yeah. So 2 million meters squared.
So that's the final answer then, 2 million meters squared.
I don't know. Did it ask for it?
Yeah.
What is the largest rectangular area that can be enclosed? Okay, 2 million meters squared.
That's a lot, right?
Yeah.
How much is an acre?
5,000 something. It's square feet too. It's
That's 6 zeros.
I don't know.
That's a lot, right?
Yes, it is. So it is a lot, especially if you have, I don't know, what does a farmer in fencing? Cows, chickens?
Very big farm.
Yeah, it's fine. Yeah, he's got some animals. All right, let's take a look at the next one now. From each corner of a square piece of sheet metal, 18 centimeters on a side, remove a small square and turn up the edges to form an open box. I actually like doing this one.
I remember doing problems like this.
Okay, so what I'm doing is cutting out some value of x from this.
Is this the box?
Yes, it
Yeah,
is.
I love the box.
Okay, so
I cried during public
I'm taking a flat area,
Okay.
cut out a corner, and that corner cut out is now going to be what dimension?
Something minus X.
It's going to be the height, isn't it? It's going to be the height. So it's going to be the height of this box. And so I'm going to maximize the volume of this now. So I should get something like this. From my flat surface, I'm cutting out a piece, and now I have a volume out of it. So whatever that piece I cut out, it's actually going to take away from my surface area, but the more I take away from that, the greater the height of my volume is going to be. So I'm going to start off with a one square, and it is 18 by 18, right? Say yes.
Yes.
Okay, good. Remove a small square from the corners. Do I know what the square is going to be?
No.
Nope, I do not. So what I'm going to call it?
Next.
X, because I don't know what that is. But it's an X by X. So the volume is equal to length times width times height. My volume is all three dimensions, right?
Yeah.
It's always three dimensionals. So length, my length, which was once 18, is now going to be 18 minus 2x. Very good. So it's going to volume is equal to 18 minus 2x. Now, what about the width? The same. Okay, it's 18 minus 2x. So I'm starting off with a square. Quite often you don't start off with a square, you start off with a rectangle. So 18 minus 2x. And what about that height? What's going to be the height? Just x. Just x right there. So, because when we go back to my little piece of paper that I made right here, so the x, whatever I cut off, it actually goes up right there. All right, so now that we have this, let's go ahead and do some distribution because I'm trying to maximize this, right? Dimension of the box with the largest volume. The largest volume. So I want a maximum of this. So I want the derivative equal to 0. So let's go ahead and do my distribution. So V is equal to X quantity 18 squared is 3. I don't know. Help me out. 18 squared.
324.
324. Okay. 324. Okay, and then it's going to be, what's that going to be? 36, 72 minus 72 x, and that's plus 4x squared. There we go. And put that other x into it. So volume is equal to 324x minus 72x squared plus 4x cubed. Here's the point where I take my derivative. Actually, let me do another page. Page. 3 what? 24.
Yeah, x minus 72x squared plus 4x squared.
There you go. All right, so now I'm going to do the derivative. So I'm going to say it's going to be dv d what? Dx, right? Because I'm taking the derivative in terms of x. 3, 2, 4 minus 144 x plus 12x squared. All right, set it equals 0, right? Set it equals 0, and I think I could factor a 12 out, can I? Yeah. Yeah. That was 18 squared, so 6 and 2, 9 and 3, 27? So 27 minus 12x plus x squared. There you go. Okay, divide both sides by 12 because we're trying to optimize this, right? We're trying to get it to the point where I can figure out my values. So let's see. I'm going to rearrange this too while I do it because I hate having the x at the end. X squared minus 12x plus 27. Factors of 27, 9 and 3? Yes. Negative 9, negative 3.
Yeah, yes.
So x minus 9, x minus 3, okay, equals 0. Yeah? Okay, so that means that x is equal to 9 and x is equal to 3. Uh-oh, I got 2 values. Only one could be the max, can it? What could I do to figure out which one's the max?
Plug them in and see which one's great.
Maybe. What else could I have done?
Well, the line.
Determine whether it's a minimum or maximum.
Yeah, to figure it out, right? I can do the line, right? Figure out slopes. Okay, I could also do second derivative, right? I know what the derivative is. I could do second derivative off of that and plug it in to see if it's min or max. Or let's go through and go back to our shape. Look at the values real quick because this is super important. This is where you're going to screw up because you have to have sense for this. And you need to make sure you're not sleeping no matter how long you're blinking. All right, so look at my values. Okay, let's plug in. The first one was 9. 9, 9. What would this be? If x is 9, what would the length be?
0.
0, right? Can I have a volume if one of my values is 0?
No.
No, I can't have a volume if one of my values is 0. So I can't use 9. So 9 is too big. So the relative domain for this, I have to say, okay, I know that x has to be between certain numbers, right? No, not an equal sign right there. X has to be between certain numbers. So it has to be less than 9, but it has to be more than 0. It has to be less than 9, has to be more than 0. because if my x was 0, I would have no volume. So my volume would go away. This is super important because I think it's even one of the questions that you're going to see on one of the AP exam type questions about relative domain. So if 9 is out of the question, that means my maximum has to be 3. The maximum has to be 3. So, and it asks for dimensions now. So I know that the height would equal 3. And then my length, what would my length be? 12. And the width? Also 12.
Wait, how do we get 12?
Because if x is 3, right? X is 3, so 3 and 3,
Oh.
yeah, that's going to be 6, or I could plug it in right here, right?
Mhm.
So it's going to be 18 minus 6, which gives me 12. All right, does that make sense? All right, good. Don't forget, like, share, and subscribe. Hit that notification button. And I think I actually did too much notes today, but we're good.